When something disturbs the membrane, that disturbance does not stay put. The membrane pushes back. It has tension. And because it is continuous, a local displacement pulls its neighbors in the same direction, and they pull their neighbors, and the disturbance travels outward as a wave. Because a wave is a ripple in the membrane, in wave physics we call that wave a ripple. A ripple is what the standard model of particle physics calls a photon. It is not a particle, nor a mysterious dual entity that is somehow both a wave and a dot. A ripple is a transient distortion of the membrane, moving naturally at the membrane's fastest speed, which is c, the speed of light in a vacuum. What are called the particle effects of light are the result of the dynamic mass created by the ripple's motion through the membrane, which we'll discuss in a later video. Every ripple has three properties that travel together. First, there is the direction of travel, what physicists call the propagation vector. Second, there is the slope of the distortion, how steeply the membrane tilts at any given point as the ripple passes through. That slope is the electric field. Third, because the membrane is a continuous sheet that resists tearing, any displacement moving in one direction requires a simultaneous lateral tension adjustment, moving around that disturbance in the opposite direction. That equalization tension can extend laterally, perpendicular to both the flow of propagation and to the electric field. That lateral spread is what is called the magnetic field. That electric field and the tension flow around anything moving through the membrane are not two separate phenomena that happen to coexist. They are two aspects of the same membrane displacement, as inseparable as the slope of a hill and the contours running across it. When the ripple stops, both vanish. The membrane returns to flat. This is fundamentally different from what happens with a stable mass, which we will get to in the next video. How long a wave lasts depends on the shape of its wavefront, as well as its amplitude. A ripple can either have an expanding wavefront, as most radio and television broadcasts do, or it can be focused, like a laser. A ripple expanding outward in all directions, like the wave from a stone dropped in a pond, spreads across a growing circumference. The same energy is distributed over more and more membrane. The amplitude, how tall the wave is, drops as 1 over the square root of the distance. The energy density drops as 1 over the distance. Eventually, any given segment of the wavefront falls below the membrane's minimum energy threshold, the quantum, and the wave extinguishes. Not because it ran out of time, because it ran out of amplitude. This limitation of expanding ripples explains the Fermi paradox, which wonders why we aren't picking up signals from other civilizations. If any civilizations out there are broadcasting their signals like we do, those signals will die out long before they reach us unless they are from one of our nearest neighbors. A collimated ripple, one focused into a beam of fixed width, does not have this problem. The energy stays concentrated. Such a ripple can travel indefinitely. This is why laser light behaves so differently from a candle flame, and why stellar signals, which must have a collimated subset of emissions, can cross billions of light years, while the unfocused bulk of a star's output dissolves quietly into the background long before it reaches us. According to wave physics, there are 4 ways that energy can move on the membrane. Radiation, which is what we have just been describing. Electrons, which are ripples that have been captured and confined inside a stable mass. Electricity, which is energy passing from one stable mass to the next, along a chain of contact, like a bucket brigade. And magnetism, which is a closed, self-sustaining circuit of energy that loops through and around a magnetic material and returns to where it started. You may recall that in a previous video, we talked about the Michelson-Morley experiment. We said the ether was real. We said there was a reason they did not find the wind they were looking for. Here is that reason. The magnetic field is the membrane's lateral tension response to any moving displacement. Physicists have been measuring it with magnetometers for 2 centuries. Every mass moving through the membrane has a corresponding tension equalization flow alongside it, the membrane's adjustment to the passage of that mass. It's analogous to a boat moving through water. At the front of the boat, there is a bow wave, and at the stern, there is an area of lower pressure. That tension differential must equalize as the object moves. That adjustment is the ether wind that Michelson and Morley should have been looking for. The maximum speed at which the membrane can equalize the tension around the smallest possible disturbance is what creates the limitation on the speed of light. Michelson and Morley were using the wrong instrument. The right instrument had been in use in physics laboratories for decades before they built their interferometer. They just did not know what they were measuring. We have been detecting the ether wind the whole time. If the membrane is everywhere, why can't we see it? We actually detect it every time we use our eyes and see any non-zero level of light. What our eyes are registering is the vibration of the membrane. Another factor is that we're looking at it lengthwise, which is its smallest dimension. If it is 2D, as we currently theorize, it would be invisible from that viewpoint, except for the out-of-plane vibrations. Because of its small scale, registering the amplitude of the waves as a visual object would require our memories to be vastly greater than they are. Imagine if we could see amoebas with our naked eyes. We would be presented with so much information every second that our brains would run out of memory capacity fairly quickly. The amplitude of the weakest waves in the membrane is far smaller than an amoeba. Why can't our instruments detect it? They do detect it every time they detect any form of electromagnetic radiation or magnetism, but our instruments were never designed to look for a 2D membrane. It may be that some future instrument will be designed to detect and map the membrane. In the next video, we will talk about persistent distortions of the membrane. Those distortions are what we call matter.